attempting to share my screen. Hopefully.
Yes, it works fine. We can see your slides.
Great. Okay, thank you. So this paper is about learning and revising temporal theories in the discrete event calculus. So the discrete event calculus is the de facto standard in common sense temporal logic-based reasoning. Most of the work on induction in this area has taken place within the field of ILP. But most of the developments in the last 30 years within the discrete event calculus are basically not studied within the field of ILP. And so what the purpose of this paper is to bring some features that ILP practitioners probably won't have yet come across, but which are regarded as essential for common sense reasoning within the temporal reasoning communities. And the two key aspects that we address in this work are the dynamic release of fluents from the law of inertia, which is what the early ILP work focuses on, which says that the truth value of a fluent shouldn't change unless acted upon by some event. So it was difficult to formalize that initially. Logic programming is a great way of doing that. But in common sense applications of this reasoning, you need to be able to release fluents from that law and bind them instead to what are called gradual change trajectories or continuous change trajectories, so that you can simulate physical laws such as the falling of object under gravity. So this is just a very, just I'm going to flash this in front of you. This is how you would model the falling of an apple. And the key point here, an apple exists, it's an object, it's in somebody's hand, its height is fixed, it's bound to the inertial law, but then releasing the object will release that fluent from the inertial frame. And then you can set up a trajectory, which basically here defines acceleration under gravity. And each successive time point, the object will basically change its height according to the law of gravitation. So this is what we mean by dynamic release of trajectories, dynamic release of fluents and binding them to trajectories. And once you have an initiates or terminates, it rebinds the fluent to the inertial frame, and then the typical initiates, terminates laws apply. So this is just to show you how the canonical discrete event calculus is axiomatized in typically answer set programming these days. And so there are basically 12 axioms, of which the first two are actually definitions. So these started in and stopped in, they're like clipped and declipped in the original event calculus. And they're used within the formulation of trajectories, which is in the axioms 2 and 3. Then you have the rest of the axioms and then some choice literals, basically. So the important thing here is that the formalization of, of trajectories involves triple time quantification once you expand the definitional shortcut of stopped in, started in. And this leads to very poor scalability in ASP tools, which leads to high grounding size and slow solving time. By contrast, the other axioms within the discrete event calculus were specifically designed by Eric Müller in order to have just single temporal quantification, and originally were designed to work in SAT solving to avoid double quantification in the original event calculus axioms. And he did that by introducing this kind of successor state version of the axioms, where the holds at just needs to refer to the previous time point in order to know what should be true at the current time point. Okay, so that's just some important information to bear in mind. Here's just a very summary. This is the tip of the iceberg of a very big discipline with lots of research into temporal reasoning that is pretty much unknown in ILP, but here are some examples of the different sort of phenomena that are modeled within the modern discrete event calculus, and it includes disjunctive events, cumulative effects, trajectories, anti-trajectories, causal constraints, effects constraints, and as well as the things on the left-hand side of the table, which have basically been looked at within ILP, but there's a lot that hasn't. And so that's why I wanted to basically bring the rest of the event calculus within the remit of inductive logic programming. It's just a summary of the different benchmarks over the years that contributed different event calculus features into the formalization. And these are all considered standard and essential for temporal reasoning in common sense domains. So what I'm actually proposing here is a generalization, first of all, of the discrete event calculus in order to take into account different policies for resolving conflicts when you have attempts to simultaneously, let's say, initiate or terminate a fluent, or simultaneously bind it and release it from the inertial frame. So there was a lot of work before the canonical formalization of the discrete event calculus, where these kind of different conflicts, there were different policies to resolve them. And one, for example, if you have simultaneous attempts to initiate and terminate, you could use that to enforce a non-deterministic choice, and that was common in the past. I myself introduced a version of the event calculus in about 2008, which basically flips the state. So this was inspired by some work by Moyle and Muggleton on kind of learning event calculus theories. So the problem with the discrete event calculus is it treats all conflicts as logical inconsistencies. And so I wanted to be able to run benchmarks that were created previously to the DEC, and so we need a way of dealing with those different conflict mechanisms. And also I wanted a way that avoids the triple quantification of time when axiomatizing the trajectories. So I basically introduced this exploratory event calculus which solves these problems, and then I show how it can be used with reasoning system Exhale, in order to, first of all, outperform current state-of-the-art approaches on standard deductive benchmark suites, and then to provide the first proof of principle demonstration of inductive theory revision in the fully featured dynamic discrete event calculus. And this includes trajectory learning, it includes learning release from the law of inertia, it includes non-determinism, etc., etc. So the fully fledged discrete event calculus. So I'm just going to flash up some results for you. This was comparing, so F2LP is the state-of-the-art translation from actually general second-order circumscriptive logic into answer set programming. And this is used with canonical axiomatization of the discrete event calculus in order to provide state-of-the-art deductive and potentially abductive reasoning services within event calculus. And although my version is more general, it has these other policies, it actually outperforms on every benchmark the current state of the art in terms of both grounding size and solving time. Okay, so I'm just going to give you a quick tour, flash through. You can look at the paper to see the detail, but basically non-inertial and inertial fluents, they're handled as normal within the event calculus. The only difference is I provide a lot of options to basically change the default policy from inconsistency if some conflict happens. And also we can choose, sorry, I can't actually see my screen over there, but yeah, we can choose if there's a start-stopped conflict, we give priority to stopping the fluent or starting the fluent or picking randomly or maintaining the status quo or flipping the status quo or simulating the classical canonical DEC and failing at that point. Then, sorry, there's dynamic fluence. So this involves sort of this release stat predicate, which has been intensively studied in the past. There's nothing extraordinary here, but the formulation of trajectory and anti-trajectory, I've basically taken the same approach Muller used to invent the discrete event calculus in the first place and applied that sort of same principle to reformulate the trajectory axioms to include only a double quantification in time. Okay, so I think this is a significant contribution which will, anyone working with event calculus who wants to include trajectories, for example, to simulate diffusion over biochemical cell membranes, something like that. So I've got about a minute to go according to my timer. So this could really help you with efficiency, I think. I can simulate class. Oh yeah. So the other thing is XEC is a native answer set program. I wrote it as an answer set program. So it is a logic programming semantics, but to simulate some of the kind of more classical benchmarks and systems for processing event calculus, there are extra integrity constraints and choice literals that we can add if we want to simulate the classical semantics. Then in the paper, what you see is a demonstration where we progressively learn, effect axioms, preconditions, non-determinism, and this culminates basically with the learning of an actual trajectory. So we set up using standard mode declarations. So here I'm using answer set programming to basically solve a quadratic equation, fit a quadratic equation to data in order to learn this trajectory axiom for some invented fluents and actions that I've made up for this running example. So yeah, so conclusion is as I started. So I think I've proposed the first axiomatisation of discrete event calculus where the handling of trajectories is only quadratic in the timeline, which is an improvement on existing work. Plus we can run all this under different policies, and that comes out in the example if you have time to go through it. And it actually outperforms state-of-the-art approaches on their deductive reasoning. But in addition, we perform full theory revision as well. So it's not just learning, it's actually full theory revision. So I can correct mistakes in the domain theory. Thank you very much.